Well, anyway, here he is, Stephen.
Thank you. Thanks for the introduction. All right, so today the session is going to be about all of the cool stuff you can do with Java on embedded devices. I have a variety of different toys here to play with, which we'll get to shortly. I have some other things on the table that you should keep away from your toys. Hopefully none of you had any accidents with coffee spills or things falling in your laptop, but we wouldn't want that on stage. That would be horrible. And today we're gonna see if Java can prevent disasters. So we're going to use the float concept in with a few different meanings. So one, we're going to try to run Java on some of these devices and see if we actually can get Java working, not sinking ships. The second thing we're going to do is we're going to chat about some of the hardware characteristics. And some of these boards have floating point hardware on them, which is kind of a pun on the word float, I guess. And the third thing is, Java's kind of like coffee, so we obviously have to do a coffee test on some of the hardware and see if it will physically float in our vat of very tasty conference coffee. So start wagering your bets now on which hardware is going to float, and we'll have some fun with the session, hopefully. This is an interactive session, so don't wait till the end to ask questions. If you guys have anything you want to mention or ask or talk about, shout it out. And if I don't know the answer, I'll find one of our esteemed Java ME product management folks who might. Oh, Terrence Barr. Thanks for joining us. All right, so first, a little bit about different size Java platforms and what runs Java. So Java actually powers a lot of different devices you might not even think about. Running from really, really small devices, things running 3G modems or point-of-sale operations, to kind of medium-sized devices, routers, hubs, other things. And then large devices like, cars and ATM machines and all sorts of high-powered devices. So the boards which I'm going to be showing you today are primarily meant for doing development on different platforms, so you can test out Java running on devices and then manufacture them in larger quantities but smaller form factors. So you can see the development boards themselves are fairly large and at times a little bit expensive, but then the chips on side of them, the chips on the board, are really tiny. It can be produced in high quantities at low costs, giving you a good way of producing Java en masse and getting it into devices of all sizes and shapes. The one board here, which is a little bit different, anyone recognize this guy? Someone shout it out. What is this?
Raspberry.
Yeah, excellent. So this is a Raspberry Pi. This board was designed more for consumer use as an end device. So it was designed by the Pi Foundation as a low-cost computing platform, but it also has a similar processor to a lot of the development boards, and it's a cool way, a very cheap way to get started with Java development on embedded. All right, so let's start with the very, very lowest powered device. So this is a Kile board. I have this guy right here. And he's running a Cortex M3 processor. Has very, very little memory on him, 120, what was it, Terrence? 128K on chip, 2 megs off, and only running 128 megahertz processor. So it's a fairly low-powered platform, but you can do a lot of cool stuff with this using Java ME 3.2 and the upcoming 3.3 release. Since he's a development board, he has lots and lots of configuration options for what you can plug into him. So some of the some of the ports on here, there's a micro SD card you can use for additional storage to add a few gigabytes of disk. A bunch of debug ports on the right-hand side, a JTAG port, Cortex debug port, which you can use to flash the device. And then for doing small testing, they have some onboard components like LEDs, joysticks, and an LCD screen. And then, serial ports for debugging, Ethernet, and some USB ports. You can use the USB ports for powering the device, and then there's a couple ports for also attaching host devices. So a fairly good platform for experimenting with the Cortex-M3 processor, but this is something you would really use in like lower-end applications where you don't need a lot of processing power. You don't run a JIT compiler on this, you just run interpreted mode only because of the constraints on memory. And you wouldn't want to do a lot of heavy processing on the board. While it's fine to do small applications where you're controlling servos or motors, interacting with other devices, it's quite suitable for that. Now, while this board is large in the physical sense, the processor on it is very low-powered. The next board I'm going to show you, so the Centurion chip, is much, much smaller. So this is the Centurion EHS5. So he's really tiny. But he's actually much, much more powerful. So this guy is running an ARM11 processor on him. And he's running at 500 megahertz. And you can actually do full Java implementations on board here. In addition to, it has onboard 3G processing on the board. So you can do applications where you're running Java on the chip itself. This is showing the backside of the board with an LGA mount, so you can attach it to other circuit boards or integrate with other systems simply by soldering it on. And one application which the Centurion folks recently got written up on was a project they did using devices like this in the rainforest to track trees and deforestation. So when you're mass producing very, very small, inexpensive devices like this, suddenly you can find new applications for it, for tracking things, talking over 3G engines, and doing simple Java processing actually on the chip. All right, so moving up on the scale in terms of size. So this is the Raspberry Pi, and a fairly nice case. I want to thank the DevOps crew. One of the guys worked at the university and had access to a laser cutter, so he took the open source box designs and custom made some boxes for the DevOps team, and I grabbed one. But this guy has a fairly powerful ARM processor. It's an ARM11 processor, ARM version 6. And you can run full Java SE on this board. So one of the big differences between developing for this board, which is a fairly constrained device, and developing for the Raspberry Pi, is you can basically take Java SE applications running on your desktop, copy the jar file over, make sure you have the Java 8 embedded ARM release, and then run exactly the same code on your Raspberry Pi. And he has plenty of input-output options for how you can hook him up to different devices. So there's a HDMI and composite out, which you can use for video, audio out, powered via USB. Your hard drive is an SD card. All right, so we have a 32 gigabyte Transcend SD card. And again, he has some USB and Ethernet ports on this guy for doing debugging. So would anyone like to see us try to get some Java code running on this guy? All right, that was the right answer. So I have some code. which is a JavaFX application, which we actually did this for the DevOps conference, but it's a fairly nice example of what you can do with JavaFX graphics on the Pi. So before we try to get it running on the Pi, let's just run this guy on the desktop and see how it works. So this was designed by Jasper, and I was hanging out in his office and brainstorming on what we wanted to do. But the idea was to create an application where we could show something visually rich, but then have it work at 1920 by 1080 resolution for large monitors outside the room at the DevOps conference. And we had Pis kind of mounted below the HDMI display to drive the display in each of the rooms. And it uses a REST interface to hook up to the actual DevOps backend. The DevOps backend has a nice REST interface we're connecting to, pulls back all the speaker data, pulls back all the session data. And here you can see Kurt Knorren's child. I butchered his name. Sorry, Kurt. And that's the current session in this room, and then the following sessions kind of go across. And Jasper and I argued a lot about little touches, like when the afterburners were on and when they were off, and the animations in and out and all this stuff. So very, very highly technical. But you can see that it doesn't look too bad on desktop, right? Fairly smooth. Animations work well, and it's nice, large format. So what do you guys think? Will it be able to run on the Pi at the same speeds? All right. So some people think it will. Some people are challenging the JavaFX on Pi. So we'll see if we can actually get it running. Oh, so. The setup here I have, let me talk a little bit about the hardware setup. So we have a Raspberry Pi, about 35 USD, fairly nice hardware for the price. We have a Blackmagic Intensity Extreme capture device, so I can capture the HDMI out of the Pi. And this is a nice like $300 capture card. And then we have a $3,000 display for our Pi. But all of this makes sense because, you guys want to see it on the big screen, hopefully. All right, so we got our SD card in, HDMI out to our Blackmagic. I'm going to attempt to share my networking. So a little trick you guys can do with the Pi. We'll see if I still have this set up from my BOF last night. So you can hook up the Pi to your laptop with an Ethernet cable, and then either on the Mac with internet connection sharing, or on Windows with, I forget what they call it, but I think it's something similar for proxying your internet. You can take your Wi-Fi or a second Ethernet card and then share the internet connection over your Ethernet. And then your computer acts like a little DHCP server and gives the Pi an IP address. And then both you can access the Pi over the network for doing SSH and getting into the device. And you can also use secure copy and copy files to the Pi, hopefully. Okay, and the last bit is powering the Pi. And this is highly not recommended. Don't do this at home. I'm powering it off my laptop with a standard USB jack, which supplies about 500 milliamps of power. The Pi actually needs 700 or more milliamps. So a good choice is to use your favorite cell phone charger or some sort of device that supplies more power. What I'm doing is not actually what you want to do. But I'm hoping that since I have no USB peripherals hooked up, it will just kind of work. And the last bit is to actually get the display up off the Blackmagic device, which this is the riskiest part of the demo, actually. And you'll notice that it completely boffs and doesn't pick up my device properly. But I shared with Garrett my little secret to this. There's the beta version of VLC lets you capture the proper resource locator string, and then you can save it off because it never changes. And then you go to network and paste it in, and oh, it's still wrong, but if you click right here, oh! All right, now we got the right. Yeah, so the Pi works great. The capture card and all that associated stuff kind of flaky. All right, so we got a Raspberry Pi login. You can see it's actually running a standard Debian Linux distribution. It runs Debian Squeeze. And I'm running the hard float version of Debian. As of the Java SE8 early access builds, the JDK now supports full hard float support. So this box, the Pi, supports full hardware floating point operations. The Kile board, which has the Cortex M3, no hard float for you. So you're going to have to run soft float and emulate floating point. And so that guy fails the float test. Oh, and I can't type in here. Okay. So rather than trying to actually type on the Pi, we're going to hook up via SSH and see if we can get that working. Oh, I need to know the IP address. Well, let's guess. Okay, that didn't work. Let's hook up a keyboard. Always have a keyboard handy when you're working with devices. All right, so it's the user ID is the very secure default Pi and password of Raspberry. Okay, and you can see we're logged in, and because I hate typing on really, really tiny keyboards, and you guys hate watching me misspell things when I mistype on really tiny keyboards, we're going to broadcast, multicast. We have no IP address yet. Thank you, Terrence. Yes, we have no IP. So it said it turned it on, even though it already thought it was on. That's entertaining. Okay, so we're going to return on the internet connection sharing. Check the adapter one more time. And now we have an IP, 192.168.2.11. Okay. All right, and now we can type on a normal keyboard and do all this great Pi stuff. All right, so the file system's here. Now I've already copied over the JDK distribution into opt JDK 1.8. We can check the Java version just to prove that this is actually the public EA 1.8.0 EA build 25-B04. And this is a full Java version. You can run pretty much anything on it. Since Java 8 bundles JavaFX, we can also use JavaFX libraries directly inside of here. So if you check the JRE lib directory, you can actually see there's the jfxrt.jar file hanging out up there. All right, and if you want to access the Pi, you can connect to it via any standard FTP, SFTP client. So I'm using CyberDuck to hook up to it. And you can see we have full access to the file system. What we're going to do is we're going to copy over exactly the same jar file So this is the devox info app out of the dist directory of NetBeans, which we compiled on desktop, and then run it on the Pi. You can also compile the code directly on the Pi, but why bother? All right, we got our app copied over. And then to actually run stuff on the Pi, you currently need to run as root user, so I'm going to run as sudo, because the OpenGL pipeline, which I'm going to be using, requires root. I don't have my paths mapped properly, but we know where it is. Bin Java. You also need to specify the javafx.platform equals open EGL, EGLFB for using the OpenGL support, and we can just give it a jar file of our devox info app.jar. All right, so that was nice. No X11 was set. Aha, don't misspell your platform, EGLFB. Okay, so that's what happens when you try to run without the EGL pipeline or the -d javafx.platform option. You get that, exactly that error. I can show you guys the error if you don't run with root 2, because that showed up on the forum several times as well. All right, so exactly the same thing running on desktop. It's loading the fonts. It's going to load all of the rooms over the web service with my proxied web connection, hopefully. And then the actual application is going to show up on the HDMI display rather than, obviously, not in the terminal. So when you're running in the EGL pipeline, it takes over the entire frame buffer of the Pi, so it will display over the HDMI or composite output and take the entire display. It gives the best performance out of the Pi hardware, but it doesn't let you, for example, embed it in X windows. There's a prototype GTK pipeline, which we use for some of our labs internally, and hopefully they'll actually release soon. Okay, so we see a little getGL error. We know that we're set. It's early access, so that's life. Okay, so this is the actual window of the Raspberry Pi. All right, so what do you guys think? Pretty good? All right, so does it float? Yay! All right, and when we were developing the application, actually we were surprised at how good the performance was. Kind of like you said, it would probably not be that good. The only thing we hit initially was with the large image size. So this is like a 1920 by 1080 resolution screen. With the large image size, some of the textures going through to the GPU caused issues. But conveniently, the guy who does all the graphics work was down the hall, and we showed him the problems, and then he fixed the build, and then now the released early access actually has all the OpenGL bugs we discovered fixed. So give it a try in your own systems and see how performance is for you, but you can do fairly nice things without a lot of optimization. This was not heavily optimized code. And we'll just leave that running for a bit, and see what other sort of toys we've got. Okay, so this guy, Beagleboard. I don't actually have one of these on me, but Garrett, who's walking around somewhere, has a Beagleboard hiding in his conference room. This board is a real development board. It's actually this first board we supported the Java SE ARM on, and it's nice in the sense it's a later ARM processor. It's a Cortex A. I forget. Anyway, one of the ARM v7 chips, which is nice, but it's kind of underpowered graphics-wise. So the Raspberry Pi graphics hardware was able to easily drive the 1920 by 1080 displays. The Beagleboard, the biggest display you can drive is a 720p display. Anything above that, and it doesn't have enough memory on it. On the other hand, this guy here, the Panda Board is really nice because it's a dual core processor. So that's this guy here. And he supports the OMAP4 specification for multimedia applications, has a PowerVR graphics chip, just like your, anyone have an iPad? Okay, so this hardware-wise, this is actually quite similar to the internals of that. And you can do a lot of cool stuff with this. This is the board that we used at Java 1 for the scheduler kiosk. We had a touchscreen kiosk attached to a Panda Board. So those are both fairly nice pieces of hardware. And there's our demo. Yay, and let's make some stuff float. You guys ready to do some buoyancy tests? All right, so I figured, you know, if we're gonna break hardware, we should be very scientific about it. So first of all, I researched a little bit why things float to make sure that we all have the same level set about buoyancy concepts. So basically, a simple model for thinking about buoyancy is when you immerse something in water. Imagine it's a cube. You have forces acting on all different sides from the water pressure. So the forces on the sides kind of counterbalance each other, right? Because you have opposing forces. The forces on the top and the bottom theoretically should oppose each other, but because of the depth, you get, so you can see the arrows on top are thinner, the arrows on bottom are thicker. So you have more pressure the deeper you go, and less pressure when you're not as deep, so it naturally forces things to rise. So the counteracting force here is the weight of your, whatever it is you're immersing. And if the weight's equal to water, then it should stay at equilibrium, so specific gravity of 1. If the weight is lighter, it should rise. If the weight's heavier, it should sink. And there's lots of other factors which have to do with whether things are going to actually float or sink, like surface tension, all sorts of stuff. But anyone actually know what these boards are made out of? Circuit boards, material-wise? Sand? Silicon? I mean, I guess like the biggest contributing factor on a board like this, let's pop this case open. This one's fairly hard to get open though. So the biggest contributing factor on a board like this is actually the wafer which is printed on. And most circuit boards, they use a material called FR4. I guess there's a whole bunch of different materials you can use for printing circuit boards, but you want something which is, fairly rigid and then won't conduct electricity, and that you can mix other materials on. So, all right, here's some specific gravities for you guys to mull over. So air trapped in the board or the case is going to make things, float naturally. And then water, that's 1. FR4, which is the board's material, is 1.85. So it's 1.85 times heavier, or will sink 1.85 times faster. And then, for example, there's a little bit of silicon, 2.33, aluminum, 2.7, copper for some of the printing, 8.96. So that gives you an idea of kind of the weights of different components. And we're not dipping it in water, we're dipping it in coffee. Does anyone want to venture a guess of what the difference between water and coffee is? Yeah. It actually, so it depends. And as any good coffee geek would know, actually, Terrence has really good coffee. So if you're ever passing through his little part of town, stop by and get a good cup of brew from his home office. It's really good. I interviewed him for the night hacking tour, and he had the best coffee on the whole tour when I was going through Europe. I think I had like 5 cups at your house in one morning. So this is some statistics from the Coffee Geek, and using the brew meter, but then I converted to specific gravity. So depending upon the type of brew, you can actually get quite varying levels of specific gravity. I mean, it's all like very low error factors, but I'm wagering like conference coffee. This has got to be like near Krups. I don't think it gets much. I'm sorry if I'm insulting Stockholm's coffee, but I'm sure you guys get much better coffee at your homes and offices than what you get at the conference. Okay, so that gives you an idea of different specific gravities. And all right, before we actually start an experiment, a little word of caution about what we're going to do. So don't do this. You're gonna destroy your hardware, and you're gonna short out your board, and cause irreparable damage to your development process. So this is highly disrecommended. But if you did want to spill stuff on your hardware, which accidents happen, you should exercise proper safety. So for the most part, these boards are actually quite safe to immerse in water and other liquids. They wash them in distilled water, purified water, as part of the cleaning process to get the solder off the boards towards the end of the manufacturing. The trick is you don't immerse them while they're on, number one. So for example, if somebody spills coffee in your laptop, the first thing you just shut the thing off, and you will likely save your hardware. The second trick is you have to be really careful about batteries. So batteries are really bad, as are capacitors on the board. So for example, the Raspberry Pi here has a nice little capacitor there, and I just unplugged it. It will likely maintain a charge for some duration of seconds or minutes or longer period of time, and if you dump it in there, you could short things out quite badly. So I shouldn't dump this in immediately. And actually, the trick is you can take a piece of metal, find your capacitor leads. There they are. And not recommended, short them out. Zzz. Okay, safe. All right, so we got a Pi to immerse in water. Let's see our Panda board. I don't see any batteries on him. I think we're safe. Oh, switches. Yeah, switches are kind of nasty. I'm gonna have to clean those out. Okay, we got a Panda board. We can toss in water, and we're not gonna dunk this guy because he has an LCD screen and all sorts of crazy stuff. And Henrik will, I think, kill me if I destroy his Kile board. I borrowed it from Henrik, so we'll stick with immersing these two guys. This one's slightly unfair because he actually has a couple screws here, so I can't get the last piece of plastic off. So this will be plus one layer of plastic, but at least no air. All right, so now you guys are armed with knowledge about this. So now this is time to place your bets about what's actually going to happen when we destroy my equipment. All right, so let's start with the we'll do the Pi second. Let's start with the Panda board because this is not really an accurate test. We have plastic attached to it. So what do you guys think? Float or sink? Who thinks this will float? Okay, a few people. Who thinks this board will sink? All right. So most people, I'd say that was like at 80% sink rate. We'll see if you guys are as good buoyancy experts as you are Java engineers. All right, you ready? This is going to make a splash, isn't it? All right. Before we start, let's move my hardware a little bit farther away from the splash zone. Oops. All right, ready, set, go. All right, that pretty convincingly sunk. All right, so good job. Most of you guys were right. Oh. All right, this is not going to be pretty. All right, let that soak there for a bit. All right, board number 2, Raspberry Pi. Now this guy does not have plastic on him. He's got quite a lot less hardware that would be heavy. What do you guys think? Is he going to float or sink? Who thinks I'll sink? A couple people. Who thinks I'll float? Oh, okay. So we got almost 50-50. All right, so this time I want to make sure this is fair. We need an audience volunteer to do the dunking. Would you care to be our here? Hey, what's your name?
Roberto.
Roberta. Thank you. So you local from Stockholm?
Yeah.
Yeah.
True.
So you have a Raspberry Pi?
No.
No. So how high should he hold it?
Okay.
Yeah. Okay. Good. Go. Oh. Yeah, that sunk. All right. So I prepared a couple conclusions because I wasn't quite sure myself without actually experimenting, and I needed the demo to work, so I couldn't try this first. So conclusion A: Java runs on devices of all sizes. Full Java SE is available on ARM processors. JavaFX gives you 3D accelerated mobile graphics. But, sadly, coffee doesn't give you these benefits. Sorry. And then, actually, if anything had floated, then we could have done conclusion B. But that's ignore that slide. And thank you for coming.